The second half of lesson 4.2 talks about a number pattern called Pascal's triangle and what is called also the binomial theorem. Right, so we're going to kind of do a quick study of these two concepts. So here is the first, actually 3 rows of a number pattern called Pascal's triangle. Right, so this would be row 0. This is called row 1, and this is called row 2. So I want you to take a moment and kind of look at this and see if you can't figure out what is going on here. And I'm going to give you row 3. So I want you to see if you can figure out the relationship of this Pascal's triangle. It's just a number pattern studied by various mathematicians. A man by the last name of Pascal claimed it as his concept, so we still refer to it as Pascal's triangle. So what we see is we see these ones, right, always on these two outside columns, if you will. But we need to figure out how do we get to our next terms, right? If I wanted to build row 4, how would I do that? And I know that there's going to be 1s on the edges, but where do I get the other numbers? I also see, right, that I have in this second diagonal here and here, right, I see that they appear to be counting by 1s, right? 1, 2, 3, so 4 would go here, and 1, 2, 3, 4 would go here, but now I'm missing this middle term. So what goes there? Well, Pascal's triangle uses addition. It adds the two terms directly above it to produce the term below it. So to get this missing term here, we are actually going to add the two terms above it. And 3 plus 3 is 6. And that pattern holds all the way through, right? Right here. 1 plus 3 is 4. It even holds for these outer rows, right? The two terms directly above here, above this 1, are 1 and nothing, right? So nothing plus 1 would be 1. So to get those terms, we add the terms directly above. And what I would like for you to do now is to build row 5. So pause the video, build row 5, and then unpause to check your work. So row 5, I know I'm going to have a 1 on the edge, and then I can just add those two above, right? 1 plus 4 is 5. I also know it is the 5th row, so it's going to have that 5 in it. 4 plus 6 is 10. 4 plus 6 here is 10, 5, and 1. So there is my 5th row of Pascal's triangle. And this has a purpose. So it helps us with what is called the binomial theorem. And so here we have, if we have a plus b to a power, right? If you have a binomial right here to a power, right? I'm talking about this part right here. We can use Pascal's triangle to help us build that solution. So the coefficients from the nth row of Pascal's triangle, the coefficients are from the nth row of Pascal's triangle. So our coefficients are going to come from Pascal's triangle. But we have to remember that Pascal's triangle starts with row 0 and not row 1. So, for example 1, we are being asked to expand p plus t to the 5th power. So, we could use Pascal's triangle to get our coefficients for this problem. And we actually just built the 5th row of Pascal's triangle, but it really does not take that much work to build out Pascal's triangle. Right? So that's row 2, 1, 3, 3, 1. That's row 3, 1, 4, 6, 4, 1. That's row 4, 1, 5, 10, 10, 5, 1. That's row 5. So because this is to the 5th power, I am going to use row 5 of Pascal's triangle. And here is what I do. I know that those 6 numbers are my coefficients for my expanded version of this. So I am going to write them down, and I am going to spread them out because there's other stuff that's going to go in between. Give myself a little more room. 1, 5, 10, 10, 5, 1. Okay? And now that I have my coefficients, okay, I know that all 6 of these are going to have a p term and a t term. So I'm going to go through and I am going to give them each a p. And when I do that, I have to remember they're going to all also have an exponent. So I'm going to start with this 5. 5, and then I'm going to decrease it. 4, 3, 2, 1, 0. Now I'm going to come back through with a T, a different color here, T, and now I have to give them each an exponent again. But instead of going 5, 4, 3, 2, 1, 0, I am going to go 0, 1, 2, 3, 4, and 5. And then all of these get added together. And now we have a big hot mess. But what we can do is work to simplify. Right? So this term right here, 1 times p to the 5th. Well, multiplying anything by 1 doesn't change its value. So I can just write down that p to the 5th. And then what is t to the 0? Well, anything to the 0 power is equal to 1. Right? So multiplying this p to the 5th right here by 1 is still just p to the 5th. And then a lot of our simplifying in the middle is really going to be very simple. 5p to the 4th times t to the 1. Well, I'm just going to write down t instead of t to the 1 plus 10p to the 3rd t squared plus 10p squared t to the 3rd. Right? I'm getting these from these terms above. Plus 5p to the 1st, which I'm just going to write down as 5p times t to the 4th. And then my last term, 1 times p to the 0. Well, p to the 0 is 1. 1 times 1 is 1 times t to the 5th. Right? That is, I know that's confusing, but that is much easier than writing this down 5 times and doing a whole bunch of foiling or something similar to that right? I don't want to do this problem that I'm writing up here, right? I don't want to multiply p plus t 5 times. So this Pascal's triangle combined with the binomial theorem allows us to shortcut, essentially, these types of problems. So looking at example 2, x plus 3 all to the 4th power, right? So this can be done with the binomial theorem. So because I have this exponent here of 4, I know I am going to be in the 4th row of Pascal's triangle. And I've already built the Pascal's triangle in the notes, so I can just steal that row. So 1 plus 4 plus 6 plus 4 plus 1. And I also know that they're all going to get an x. Right? From here, I pass out the exponents. 4, 3, 2, 1, 0. I also know they're all going to get a 3. And I know those 3's need exponents. And I go backwards. 0, 1, 2, 3, 4. Now, because in this binomial I have a constant, right, I'm going to actually get less variables and more just number answers. Right? So 3 to the 0, anything to the 0 power is 1. X to the 0, I'm going to use that later. Anything to the 0 power is 1. Right? So I can use that and start simplifying as I go. 1 times x to the 4th times 1, right? Because this is equal to 1. So that's just x to the 4th. Well, 3 to the 1st, right here, is equal to 3. 3 times this 4 is 12. X to the 3rd. Here I get 3 squared is 9. 9 times this 6 is 54. X squared. 3 to the 3rd would be 27. 27 times 4 is 108. X to the 1st, or just x. And then 3 to the 4th is 81 times 1 times 1. And that's it, right? Much simpler than x to the plus 3 times x plus 3 times x plus 3 times x plus 3. Right, so that is a quick look at Pascal's triangle and the binomial theorem.